First of all, I would like to welcome you all to this fifth webinar of the graduate program in physics of the Federal University of Pará in Amazonia, Brazil. So today we have the honor to listen to Professor James Maxwell Bardeen, who is a member of the U.S. National Academy of Sciences. Professor Bardeen has never visited our graduate program in Amazonia, what makes this occasion an even more privileged one for us. Professor Bardeen received his PhD from Caltech under the direction of Richard Feynman. Professor Bardeen is an Emeritus Professor of Physics at the University of Washington in Seattle. Borrowing an introduction from the Perimeter Institute, where he has given very nice talks, I can mention that Professor Bardeen has made major contributions in general relativity and cosmology, including the formulation, together with Stephen Hawking and Brandon Carter, of the laws of black hole mechanics, what is related to his talk today. In one of Professor Bardeen's seminal publications, he introduced in 1968 a black hole line element without a central singularity, which became known as Bardeen black hole or regular black hole. Some people from Pará University and other places in Brazil, including myself, have studied physical phenomena around this kind of black holes, what makes this occasion even more special for some of us. I know that you are here today to listen to Professor Bardeen, so that I should not take more of your time with this introduction. Let's make it short. Professor Bardeen, thank you once more for having accepted our invitation. The audience is yours.
Okay, well, thank you for inviting me. It's an honor, and I hope you enjoy the seminar. So the question of the quantum properties of black holes is something I've avoided for many years until the firewall proposal came out about 8 years ago. And I thought that sounded pretty ridiculous, so I decided to get back into it. But I have to start off by admitting I am no expert in quantum gravity or string theory or ADS-CFT. My background really is more classical general relativity, but you know, I hope I can serve a useful purpose just by calling out what it seems to me not sensible results. Anyway, so let's get started, and this is the outline. I'm going to review just the classical properties of black holes as they're developed in the late 60s and early 70s. And then, of course, the landmark event was Hawking's announcement of Hawking radiation, which really made black holes thermodynamic entities as well as just entities in classical general relativity. So we'll review the properties of Hawking radiation, and then I'm going to talk about of course, the discovery of Hawking radiation set off 45 years of controversy over the black hole information problem and so on. But I'm not going to try to go into that in any extent at all, and just talk about a couple of proposals, relatively recent proposals, which in very different ways try to solve the black hole information problem. So the first one is a very interesting new work came out a little over a year ago, and there's a very nice review of this in this paper I cite by Harry et al., which just came out recently, and this proposal is based on what many people have sort of automatically assumed, which I don't think is correct. But anyway, they've automatically assumed that the number of degrees of freedom, quantum degrees of freedom of a black hole is bounded by its thermodynamic entropy. Now that's true for ordinary quantum systems, but I don't think black holes should be considered an ordinary quantum system. So, but anyway, it's an interesting proposal, and based on the idea of CFT and some things called quantum extremal surfaces. I'm not going to go into it in any detail. I don't really understand a lot of the details in any case, but it is an interesting way, possibly, of in that consistent with the central dogma for getting information out of the black hole. So now the other approach I'm going to talk about is based on liquid quantum gravity, loop quantum gravity, and the idea is that unlike often assumed, there is no black hole event horizon. That the singularities in the interior of the black hole, classical singularities, can be resolved by quantum mechanical back reaction, and the quantum information trapped inside the black hole can evolve, can pass from the black hole into a white hole without a singularity. And all the trapped information, quantum information, can then escape from the white hole horizon. And in this proposal, the central dogma is not true. The von Neumann entropy of the black hole can be vastly exceed its thermodynamic entropy, the Bekenstein-Hawking entropy, and near the end of the black hole evaporation. And but this is a way, I think, what I consider a more straightforward way of preserving unitarity and solving the black hole information problem. Okay, so let's get started then. So, this, quick reminder of how things developed in the 1960s, which I was fortunate enough to be, in the early 70s, which I was fortunate enough to be part of. And so the Schwarzschild vacuum solution of classical general relativity had, of course, been known ever since 1916. But its full appreciation of its global structure and its non-singular event horizon at R equal 2m was only really fully achieved in the 1950s. But still, it was a spherically symmetric solution, which is obviously not generic. And so the question then was, what happened if, say, a star, two masses turned into a white dwarf, or as was discovered in 1968, a neutron star, if that would collapse, then what would happen? And now the seminal discoveries that fuel this development are the 1963 discovery of the Kerr solution, which is axisymmetric and has two parameters, mass m and angular momentum j, which has an event horizon for j over m squared less than 1, and I'll be using units for the most part of just g equals c equal 1, standard GR units. So that this had a non-singular event horizon, screening interior singularities from the outside universe, and the accretion of matter across this event horizon could be a very powerful energy source for things like quasars and radio galaxies. And of course, the other thing that happened in 1963 was the discovery of quasars. So the need to get a very compact, enormously powerful source of energy, and then really spurred for these astronomical explain these astronomical observations, then really fueled things in terms of the theoretical development. No, and so another key development was the Penrose Singularity Theorem. This is in classical GR, and if you assume just the null energy condition, which is that this as projected onto any null vector, the stress energy tensor in GR is that projection is non-negative, greater than or equal to 0, and that's classically seems a very reasonable energy condition. And you also have to assume a non-compact Cauchy hypersurface. That is, Cauchy hypersurface is a space-like hypersurface, which from which future events, any future event in the space-time, the past light cone from that event intersects the whole past light cone intersects this hypersurface. So that makes the evolution of the space-time predictable, but the key part of it is non-compactness, but that seems very reasonable in an asymptotically flat space-time. Okay, so and then and what that theorem says then is once you get a trapped surface, which is a closed two surface from which both the inward and outward normal null geodesics initially converge, then there must be a singularity in the space-time in the sense that some of these geodesics cannot be continued to infinite affine parameter. And there's a contradiction if they can't. If you assume they can be, there's a contradiction. So so then this suggested then that you get trapped surfaces, then you have a singularity, but then the question is, what does that mean in terms of the evolution of the black hole? Well, so there's the cosmic censorship conjecture, which says that any such singularities are hidden behind the event horizon for generic evolution of the space-time. And that's still a conjecture, but I think it's reasonable. And the other is that thing that could happen to get around the Penrose theorem without a singularity, and that's behind what the example that I proposed in '68, which we mentioned, and that is the existence of a Cauchy horizon, which, but that if you are trying to explain unitarity of quantum evolution of black holes, a Cauchy horizon is the last thing you want, because it makes the evolution unpredictable beyond the Cauchy horizon. So, so this is of course, the way of diagnosing these spacetimes is usually used as what are called a Penrose diagram, or is in which you sort of conformally compactify in terms of coordinate transformation, not physically, but the coordinate transformation, the space-time, in such a way that that in this diagram, so for spherically symmetric space-time, radial null geodesics are just 45-degree lines. So we have outgoing radial in this region here, which would correspond to the asymptotically flat universe. Outside the black hole, we have outward going null geodesics are this way, and ingoing radial null geodesics are this way. And and then infinity is by this conformal transformation is brought into a finite radius and a finite coordinate location. And this is past null infinity. So null geodesics, ingoing null radial null geodesics start at infinite radius and go inward, and then they cross this null hypersurface, which is the black hole horizon. And then inside that black hole horizon, there are trapped surfaces. And so the Penrose Theorem applies. And we get without, in the case of Schwarzschild, we get a singularity at r equals 0. And then this line is the future null infinity, where so outgoing radial null geodesics go to infinite radius at this point on this line. Okay, now if we're talking about a black hole formed by a collapsing star, then this blue line represents the surface of the collapsing star, and everything to the left of that is no longer Schwarzschild's. Disregard everything to the left of that blue line. Of course, you have to then consider what happens to the interior of the collapsing star, and there's, given the Penrose singularity theorems, we expect that to be singular as well. Now, of course, people have considered the full analytic extension of the Schwarzschild solution in its own right as something to consider in general relativity. But I'm going to be focusing on what I consider real black holes, which are those which are formed by gravitational collapse. That's a finite time. Okay, so now, sort of in some ways, the culmination of this development of the classical theory of black holes was formulated when there's Bardeen, Carter, and Hawking paper, which came out of the Jesus Summer School of 1972, which was a real, wonderful getting together of most of the leading researchers in black holes, classical black hole theory, and in this we considered Kerr black holes, which so consider a Kerr black hole, which by then was thought to be the unique solution to general relativity, which had a non-singular event horizon and no singularities outside the event horizon, and stationary and axisymmetric. So, all right. So now the Kerr metric then is, so what we consider then considered as having a Kerr metric in a stationary state. Then you throw in a little bit of matter or do something, throw gravitational waves in or something to perturb the Kerr black hole, which then settles back down into a new Kerr black hole with a slightly different mass, dm, change in mass, dm, change in angular momentum, dj, and change in the horizon area, dA. Now, another property of the black hole is what's called its surface gravity. And its angular momentum, angular velocity, both of which are defined from the two killing vectors of a stationary axisymmetric black hole. So for the Kerr metric horizon, we can calculate this as essentially the gravitational acceleration of a zero angular momentum observer at the horizon, and sort of redshift, which is actually infinite, basically, if the observer is static. But then we redshift it to get a finite quantity, and Now, for the social black hole, and I'm going to talk mostly about social black holes in this talk, just because they're simpler. The surface gravity is just 1/4m, which is m over r squared at the horizon. So, and of course, social black holes have zero angular velocity. All right, so the zeroth law says that the surface gravity is uniform over the horizon, and this is derived from the Einstein equations. And and of course, that is analogous to the zeroth law of thermodynamics, which says that temperature is uniform for a body in thermal equilibrium. The temperature is uniform. And then we have the first law of black hole mechanics, which says that the change in mass or change in energy of the black hole is this kappa over 2 pi times the change in area minus omega dj. And this looks just like the first law of thermodynamics, in which the change in internal energy is TdS minus PdV, and PdV gives a work. This is sort of a work term, analogous to PdV. So now the second law of black hole dynamics, black hole mechanics, is that dA, the change in area, has to be non-negative. In other words, the area of the horizon cannot decrease as long as the null energy condition is satisfied by any matter that crosses the energy crossing the horizon. Okay, so, and then of course there's the fourth law, by analogy with thermodynamics, should be that you can't reduce the surface gravity to zero by any finite process, analogous to not being able to reduce the temperature to zero in ordinary thermodynamics by a finite process. So the point is, these have the same form as the four laws of thermodynamics. If you somehow interpret the surface gravity as being like a temperature and the area being like an entropy. But you say in the paper that black holes are black, don't have a temperature, and of course that turned out to be wrong. And Jacob Bekenstein at the same time, with maybe more physical insight, was arguing that, and developing arguments that to preserve the ordinary second law of thermodynamics in the presence of a black hole, you had to associate an entropy with the area of the black hole horizon in Planck units. And the argument basically was that if you throw matter into the black hole, it takes entropy with it, and the entropy of the outside region outside the black hole decreases, and this would violate the normal second law, unless you say, but it also increases the area of the black hole, and so what he suggested then was that there was a generalized entropy, which is this given by something times some numerical coefficient, which he tried to estimate, but didn't really have a good way of estimating exactly what it was, and times the area divided by h bar, plus the thermodynamic entropy of all the exterior matter. And then what the law he proposed was that this generalized entropy would be non-decreasing. Well, so about a year and a half after a paper came out, Hawking, at having tried to do looking at quantum field theory and on the black hole geometry, show that black holes in fact are not black, as explained in the initial announcement. He talked about black hole explosions were small primordial black holes in the early universe, but and the detailed arguments are laid out in a 1975 paper. It's a classic, really classic paper, which really made him immortal in some sense. So and the basic idea in this paper, the results of his calculations, is that vacuum fluctuations in quantum fields in the vicinity of the event horizon, say a Schwarzschild black hole for simplicity, but the diagram applies to other black holes as well, part of which end up propagating out to large radii, and part of which end up trapped inside the black hole, and the part that goes off to large radii carries positive energy with it, and the spectrum of these Hawking quanta going off to infinity is a thermal, close to a thermal spectrum, and corresponds to a temperature which is equal to this h bar kappa over 2 pi, and h bar over, which is h bar over 8 pi m for Schwarzschild. And this shows that the first law of thermodynamics now can be considered a real thermodynamic relation, and the thermodynamic entropy of a black hole is then, it's called the Bekenstein-Hawking entropy, or SBH, is the area over 4 h bar in Planck units. So in standard ng equals 1 units. So, and then he also showed that to reach Hawking quantum radiated, there's a negative energy, this negative energy relative to infinity, Hawking partner, which is left inside the black hole, reducing the mass of the black hole. And of course, that is what you need, because you certainly have to have overall energy conservation in the process. So, so the mass of the black hole decreases as this Hawking radiation streams out to large radii, out to infinity, future null infinity. And he also, but this Hawking quanta are, he showed, are uncorrelated like a normal thermal radiation, and that therefore the entanglement entropy of the radiation as a non-zero entanglement entropy with what's inside the black hole, and it steadily increases as you get more and more Hawking radiation. So and the spectrum of the Hawking radiation is said roughly thermal, but what that means is that at high frequencies, this is the Planck spectrum for, say, photons and gravitons, but is modified at smaller frequencies, such as omega m is less than 1, or in other words, wavelengths more or less larger than the radius of the black hole, because modes, those modes don't freely propagate there's a potential barrier near the horizon, which means some of them get reflected back into the black hole. So, and so then there's a somewhat complicated calculation to find the actual net luminosity of this process. Then these calculations were done for photons and gravitons by Page and certainly afterwards. And basic form is that the luminosity, or the energy lost unit time at infinity, is a coefficient Q times h bar over n squared, basically, or 2n squared. And that's roughly what you expect from thermal radiation using the Stefan-Boltzmann law. So actually the area of the effective area for the radiation is not the horizon area, but is the radius of the circular photon orbits the radius of the black hole shadow, whatever you want to call it. So the and this means then that you get a time scale for the you get steady loss of energy from the black hole. It evaporates on a time scale which goes as n cubed over h bar, and the initial mass cubed over h bar, and that's enormously larger than the age of the universe for any, even for a one solar mass black hole. So for any of the known astrophysical black holes, this is pretty negligible, and in fact, any black hole in the real universe is not losing energy; it's gaining energy because it's absorbing, if nothing else, the cosmic microwave background radiation. Now, okay, so now there's some aspects of this which I consider the way they were initially presented by Hawking, and largely for many people considered just without question as properties of evaporating black holes. And so the first myth is that Hawking radiation is the result of pair creation in some very small region straddling the horizon, with the Hawking partner having, well, it has to have negative energy, negative killing energy in the curved space-time, or in other words, negative energy relative to infinity is measured at infinity. Locally, it can have a positive energy if it's inside the black hole, and on an outward radial motion, just inside the horizon, would have positive energy. All right, so why is this wrong? Well, one reason I consider is that if you calculate the normalized stress energy tensor in the semi-classical approximation it's called the Unruh vacuum state, which corresponds to what should be the case for a black hole that's formed by gravitational collapse, that and settle down into the stationary state, approximately stationary state. Then it shows what this normalized stress energy tensor shows. It's not an outward flow of positive energy starting right at the horizon, rather than that as you get close to the horizon, within roughly r equal 3m, the net flow is inward flow of negative energy, rather than, and this, you have the same positive energy flux in both cases, but depending on the rest of the stress energy tensor, you can either have outflow of positive energy or inflow of negative energy. And so what these semi-classical calculations go, and of course Hawking's calculation was a semi-classical calculation, that there's inflow of negative energy near the horizon, which is inconsistent with something happening very close to the horizon that generates the Hawking radiation. So having a way, I would think this is a result of tidal disruption of quantum fluctuations outside the black hole, and with part flowing out to infinity and part in with positive energy and part flowing into the black hole, negative energy. And actually, there's a very recent paper by Stephen Giddings, who's a famous black hole theorist at Santa Barbara, which makes a similar argument. And I have this archive reference for by citing the normalized stress energy tensor calculations. All right, so a second myth then is that the quantum related to this is the quantum information associated with the von Neumann entropy, or the Hagen entropy of the black hole, that's been trapped by the black hole. The myth is that this stays and propagates right along the event horizon, just inside the event horizon, and that and this is assumed because people wanted to somehow be able to get this information out in the Hawking radiation, later Hawking radiation, and late Hawking radiation, and that was only seemed possible if you had the black hole, the information propagating very close to the event horizon. So you can imagine some quantum process at the horizon which would allow that to escape, violate this classical causality. All right, so now what I argue against that is that if you consider even so, it looks like from the semi-classical just energy tensor calculations, so what's actually happening is that negative energy is flowing inward along inward radial longitude S6. But even if you say that somehow it's converted to outflow along outward radial longitude S6 inside the black hole, these don't stay close to the horizon. Once they're a finite distance inside the horizon, they reach in the case of Schwarzschild, they reach the oracle zero singularity in an advanced time interval of order a few times m, and this of course is tiny compared to the total evaporation time, and now of course what you then can argue is that, well, you can maybe still restore unitarity if quantum fields can violate this null energy condition, so that the classical singularity theorems do not apply to black holes in taking into account quantum effects. And now there have been claims that even in quantum field theory that there are singularity theorems for black holes, and these are based on what's called the quantum focusing conjecture by Bousseau et al., which is just conjecture, and therefore you don't have to believe it, and a proof of the generalized second law by Wall, but he used semi-classical arguments, which certainly break down as you get close to the oracle zero singularity. So neither of these, I don't believe either of these have any need to believe either of these theorems. And people in loop quantum gravity community have argued that the singularities can be resolved in quantum gravity, and that means the quantum information can escape eventually. So anyway, so this is the Penrose diagram that Hawking published in that 1975 paper, and a huge number of papers ever since have quoted this same diagram, more or less. So what Hawking suggested then was that you have the event horizon here, collapsing star, event horizon, and for at least for circle symmetry, an oracle zero singularity. So he's saying the singularity is not resolved, but the black hole evaporates down and disappears when it gets down to the Planck scale, leaving nothing behind, and you just have this oracle zero here is just the origin of a flat coordinates, flat ordinary coordinates, circle coordinates in flat space, and the Hawking radiation streams out. Then what happens to the partners inside the black hole? Well, they apparently just get absorbed by the singularity, and this is what led Hawking then to suggest that black holes caused violations in the evolution of the quantum mechanical wave functions of the if there's a black hole. And he held to that position for a long time. And but then the question of how you get the information of the Hawking partners out has been this raging controversy over the last 45 years. And now Hawking eventually conceded that you should have unitary evolution of the quantum system, even for a black hole, but that was not until 2005. So the question then is how you can make the properties of the black hole consistent with unitarity, and if the black hole does evaporate completely, then how you get a final, and you started from a pure state. Unitarity says you should end with a pure state, but so how can you have a final pure state? And so as I said, Hawking partners, I think, end up deep inside the black hole. I don't believe the quantum information will be stored on the event horizon, at least maybe a little bit, but not very much. And so, but then a key issue is whether the black hole is a normal thermodynamic system for which entanglement entropy can never exceed the thermodynamic entropy. In other words, the thermodynamic entropy is supposed to be correspond to the total number of degrees of freedom in the thermal system, and the entanglement entropy cannot be greater than the number of quantum degrees of freedom. So this is what this basic assumption is. What, as I said, was called a central dogma. And there's some examples from string theory which seem to be consistent with this, but only for an extreme black hole and using for certain special string theories. But given this hypothesis, the trapped quantum information must start being released by what's called the H time, when about half the black hole is when the black hole has lost about 1/2 of its mass. And initially large black hole then is still very large, and you would think a semi-classical approximation would still be valid at that point. Alternatively, black hole retains its quantum information and evaporates down to the Planck scale, but then its entanglement entropy, or von Neumann entropy, FBN is for von Neumann, is of order the initial at the end of the black hole evaporation. The von Neumann entropy is the order of the square of the mass of the black hole divided by h bar, sort of the initial mass, or which is huge compared to the Beckstein-Hawking entropy at that point, which is, for a Planck scale area, is of order 1. And so then you have to assume that quantum backwardation can resolve the interior singularities, and in particular allow the black hole to evolve into a white hole. And this has been suggested by a lot of people and that just requires new physics at the Planck scale. It doesn't require modifying drastic new physics at the event horizon of a large black hole. So this is what then you expect for the evolution of the entropy. You have this is finding things as a function of the fraction of the mass that's been radiated, essentially, and so we have the Beckstein-Hawking entropy decreasing quadratically. It's quadratic in the mass, and that's the green curve, and then the von Neumann entropy, and this is not the result of some accurate calculation. It's just sort of a fudge for the fact that page showed that the unknown entropy is equal to the background entropy at half the masses and lost. So, so then the question, either the unknown entropy keeps increasing while the background entropy goes to zero, or as is usually been argued in a lot of papers, the unknown entropy has to start decreasing at that point where they cross, and has to follow the Beckstein-Hawking curve down to zero at the end of the black hole operation. Okay, so how can this be? Well, so about a year ago, Pennington and a group with the lead author of Mary came out with proposals, similar proposals, and published at the same time. And I just refer you to this review, which is done by Mary et al., which is in 2006.068, very recent, came out in June. So these are both papers based on the central dogma. They use ADS-CFT and assume, for simplicity, circular symmetric geometry. So, so the argument is roughly that you consider the region inside of some cutoff radius, a fairly large radius, but not infinite radius, the generalized, and consider the entropy of that region. And they argue that you can then consider this generalized entropy I mentioned before associated with some two-surface X on a Cauchy hypersurface sigma. And this two-surface divides the sort of concerning a space-like slice of the space-time, which divides an interior region and an exterior region. And this generalized entropy, of course, has the form S-gen is the area of the two-surface divided by 4gh bar, plus the external unknown entropy. And for x equal h, for x on the horizon of the black hole, this is the black hole generalized entropy, but this is a more general kind of non-arbitrary two-surface. So now what we do is we, on a given Cauchy hypersurface, which is anchored at some fixed advanced time at this cutoff radius, we minimize this generalized entropy on a particular choice of Cauchy hypersurface to the interior, and then maximize it over all choices of all slices which intersect this cutoff radius at about slightly less than this advanced times nu c, and are continued into the black hole. Now, what they argue then is that if there's an extremum, or a particular minimum of this, there's an extremum of this generalized entropy defined in this way, then that equals the entropy of the region. And this is right from ADS-CFT, basically. So early in the black hole evaporation, you have all the Hawking quantity inside the region. The entropy in the region is zero because if you have a pure state, say assume a pure state initially. Now, if you assume that the Hawking partners do propagate just inside and along the black hole horizon, then by the page time, there is a quantum extremal surface just inside the black hole horizon. at the time, this advanced time, corresponding to what you defined at the cutoff reach surface. And this, and then this, because it's inside the horizon, this extreme entropy, SXTR, is less than or equal to the Bekenstein-Hawking entropy. So if this is the entropy of the region, then that's less than the Bekenstein-Hawking entropy. Now, and they have arguments based on quantum gravity path integrals involving very complicated path integrals involving multiple replica wormholes. But still, I think what seems to me is that their construction seems to require that Hawking partners remain close to the event horizon, which I argued was not true. Okay, so now let's say a little bit about the alternative from loop quantum gravity. So, and if you ask, normally you think of a limit on the number of quantum degrees of freedom in a certain region as being limited by the volume density, and there's no more than 1 degree of freedom per Planck volume, basically, and not per Planck area, which is the Bekenstein-Hawking formula. So what is the volume of a black hole? Well, and then this is something that's been argued previously by other authors like Rovelli and Trickler. You can talk about a physically meaningful volume by considering a maximal hypersurface, which has trace k equals 0. And this is because otherwise you can have a surface which is almost null and get arbitrarily small volumes. But now if you argue that what happens in spherical symmetry at r equals 0 is that there's a minimum circumferential radius at that point, and the black hole evolves into a white hole, then you can ask, what is the volume on that transition surface? And of course, slices earlier in the collapse, as you go to the future inside the black hole, you get smaller and smaller volumes. But this is supposed to be then a lower limit to the volume in something like a maximal hypersurface. So, and so now I'm going to just assume that this is a generic circumsymmetric metric in an advanced time coordinates and the coordinate z, and except for the fact that I'm going to say the circumferential radius is z squared plus a squared. So it's equals 0. There's a minimum circumferential radius, and that's the transition presumably from the white black hole into the white hole. So, so this now. So you can argue then that, so what's the volume of that surface? Well, the volume is the two-sphere area times the proper distance along the surface, which, and the proper distance is this e to the psi times dv, and I'm going to assume that each psi is no smaller than a over m, and there are reasonable arguments for that, though certainly not airtight. And now a may be dependent on the black hole mass, and most of the loop property gravity people assume that for a massive black hole, a is the radius at which the curvature becomes Planckian, which is much larger than the Planckian value for the radius. But as the black hole evaporates down to the endpoint, that in any case, as long as a squared is greater than h bar, and even psi is greater than a over m, the number of degrees of freedom which reach c equals 0 in advanced time dv, assuming they propagate along ingoing radial geodesics, is dn, which is luminosity dv divided by the Hawking temperature, very crudely, and that's less than dv over m. And if you then compare that with the total volume, the volume occupied by those degrees of freedom, it's less. The ndv is less than 1. So over the lifetime of an initially large black hole, the volume increases enough to accommodate all of the Hawking partners. You don't need to, without any, in terms of the volume density of the quanta, there's no problem. And furthermore, the quanta that fall into the black hole and cross this transition surface early in the black hole evaporation are at an enormous space-like distance from the black hole horizon near the end of the black hole evaporation. And so near the end, there's no reason to think there's any sense in which there's any real thermal system which encompasses both the horizon at the end of black hole evaporation and the interior at early times. So, and the quanta at early times, if they cross into the white hole, they can escape from the white hole and don't have anything to do with the horizon at late times. So, all right, so say a little more about this black hole to white hole issue. You can read this. There have been a number of proposals in the literature for just trying to model this, how this happens for loop quantum gravity. None of them I consider very satisfactory. They don't agree with each other, for one thing, and in terms of what the quantum corrections really are, particularly at large radii, and none of them really deal with the black hole evaporation. They basically consider the mass stays constant, and don't deal with the end of the black hole, how the black hole ends. So I tried to take into account evaporation in a very crude hand-waving way by just considering an ad hoc effective metrics of the form given in this form, and which and then in the black hole, you have advanced time as a coordinate, and the assuming the partners propagate at constant retarded advanced time, then there's a mass parameter which is a function just of advanced time in the black hole, and at the transition surface, you want a space-like transition. So you have GZC is less than 0, it's equals 0. But, and then the black hole ends and the white hole begins for external observers as GZZ goes to 0, it's equals 0 at a particular point, and a squared is of order h bar. So the trapped quantum information then propagates across this transition surface and into the white hole. And this is all described by a Penrose diagram of this form, where you have the black hole horizon here, the transition surface, article A, is some interior, which I don't try to deal with, interior of the collapsing star, and then the white hole, and you have trap surfaces here, anti-trap surfaces here. So here, any geodesic has to know any causal geodesic, any time like, and any null geodesic has to goes to larger radii, superficial radius, and here, as opposed to the black hole case. And there's no barrier to anything, things crossing the white hole horizon. This is the white hole horizon, and so you can have things stuff crossing the white hole horizon and going off to infinity. The black hole ends here, and you just maybe have some quantum corrections to the geometry, but no longer any, no trap surfaces or anything, just decaying quantum corrections going off to infinity after the black hole ends. And now there are issues, significant issues here. Now, if you say, question is how does things propagate? The negative, so the Hawking partners have negative energy relative to infinity. How do they propagate inside the white hole? Well, one possibility is that they just propagate along constant retarded time inside the black hole and just go off to infinity. But if they carry the negative energy with them, that means the mass of the white hole, which is sort of Planck scale here, and increases as you go and becomes something like, by the time it intersects the collapsing star, now expanding star, you have, you have the masses of the white hole is back to the original mass of the black hole. But the problem with that is that you violate minimum energy density conditions that derived for quantum fields in Minkowski space-time in this asymptotic region. There's the negative energy density, sort of the flow of negative energy falls off too slowly to be consistent with those theorems. So then what happens, the alternative is that the negative energy stays inside the white hole until it eventually reaches, ends up with the collapsing star. And but you still want to have a quantum information going off to, in a steady way going off to Sky Plus. And now there's no causal barrier to that. And if you ask what happens to ingoing radial null geodesics inside the white hole, it turns out they all converge exponentially on the white hole horizon. So you end up in the way that's hidden by the Penrose diagram, you end up with a thin shell of all these Hawking partner of negative energy just inside the white hole horizon, and then so that's just inside the white hole horizon. But then if you have vacuum fluctuations propagating this along outgoing radial null geodesics, which you certainly do, this can then interact with that shell and carry entanglement entropy off to infinity without, quantum information off to infinity without any negative energy. Now you do have to have some initial outflow of negative energy just after the white hole was born, but for most of its lifetime, that would stay sort of a Planck scale radius and mass. Okay, so those are alternatives. I don't have any real rigorous way of proving any of that, but anyway, so just wrap up here. I'm out of past time, but we have so the controversy over black hole information is still far from over. There's enormous literature. Papers are coming out all the time in the archive. Almost every day there's at least one or two papers dealing with the black hole information problem. So, but on the other hand, there are also different ideas which I haven't mentioned. Such as fuzzballs or graviton stars, in which there never is a black hole horizon. There's some sort of phase transition which prevents the horizon from forming, even though it's at a large scale where you expect quantum gravity corrections to be small. So, now some people are certainly very interested in whether they can observe any quantum effects in the new observational data that's becoming available, like detection of black hole gravity waves from black hole mergers and or imaging of black holes from the Event Horizon Telescope. And there's hope they can provide some clues, though I'm not holding my breath. It's unlikely that there'd be quantum effects on such large scales. So that would be large enough to be detectable. So the one thing that could shed light on a lot of light on all this is if we were lucky enough to see the last stages of evaporation of a primordial black hole, but we don't know that any such black holes exist. And so far, there's no evidence of that. So theoretically, what we need is a definitive theory of quantum gravity. But again, we don't seem to be very close to that. It's just, there are different schools and different ideas, but nothing that really hangs together as widely accepted theory. Okay, so, and there's a recent quantum gravity conference at Perimeter, I might mention, which did bring together representatives from both string theory and liquid quantum gravity, and loop quantum gravity. I don't know, I see liquid, but loop quantum gravity, and the videos of the talks there's some very good talks there, which are posted on their website, so I could recommend you look at those. Anyway, thank you very much for your attention, and
thank you, Professor. I ask everybody to turn on their microphone, clap our hands, and thank Professor Bardeen. Microphones again. Thank you. So let us now have some questions. So for those who want to make questions, I ask them to write down in the chat. If you want to do the question yourself, please just tell me by the chat, I have a question, and then I will give the word to you. So while we wait for the questions, let me tell you, Professor Bardeen, that it has been a wonderful talk. This is not only my opinion, many people writing that in chat. And I should say that, well, this is originally a webinar from the Belém graduate program in the north of Brazil, in Amazonia. But we have, Brazil has around 25 federal units, and we have more than half of them represented in the audience of your talk. So most of the time, your audience oscillated around 200 people, but not only from Brazil. I could go through what people have written their names in the chats, and some of them I know. I can tell you that there's people from Spain, India, Portugal, France, USA, England, and Chile. The ones that I have spotted, right? But so let us go for the questions. So the first question registered is from Parto Majundar. Parto, I'm worried about your sound. Whenever you turn on your sound, it gets very, very loud. Do you want to try it? So turn on your sound and please make your question.
Am I audible now?
Yeah, it's
am I audible?
yeah. So,
okay.
So maybe Pato, if you don't mind, can you please write down your question and I read it for you? Because
No,
it's very high, the sound. So in the meantime, let me pass the word to George Zanelli. Zanelli, could you please turn on your sound and make your question?
Okay, hi. Professor Bardeen, thank you very much for a wonderful lecture. I have a question which is mostly, it's the idea that you have unitarity in quantum mechanics is something that is very deeply rooted in most of us. We believe that. But the thing is that in order to prove the unitarity in quantum mechanical systems, you need to have a well-defined Cauchy problem essentially in Rn, in a flat space. Whereas we try to extend this idea to a curved space and even more to a multiply connected space like black hole geometry or Kerr geometry or so forth. So is it possible to actually prove that there is unitarity in a space like that for an elliptic operator or something?
Well, I would say that if the space is really multiply connected, then no, you can't have unitarity. You have Cauchy horizons, and that removes any possibility of having some well-defined global unitarily evolving wave function. So, on the other hand, the models that these loop quantum gravity models I was discussing with black holes going to white holes, the topology of the space is just Minkowskian. I mean, the Penrose diagram is basically the same as Minkowski, except for what goes on in the interior of the black hole. So the asymptotic structure is Minkowskian. So that would allow that unitarity could be preserved. Now, again, whether unitarity really is consistent with quantum gravity in some general sense is, I think, an open question. I mean, I don't think we understand quantum gravity well enough to say. Now, it is true that in ADF CFT, you have this duality between a quantum gravity theory, maybe not the correct one, in the bulk, which is a string theory in the bulk, which corresponds to quantum gravity and some limit, dual with this conformal field theory on the boundary of an ADS spacetime. And now this conformal field theory is explicitly unitary, right? So if there is this, given this duality, then it says that quantum gravity, or at least in what this theory would say is the quantum gravity in the bulk is also unitary. Now, of course, we don't live in an ADS universe. And there are, so I think it's just conjecture that applies to sort of real quantum gravity in our universe. So, but it is, some sort of indication that maybe you can have a unitary theory of gravity, quantum gravity. So, but that would mean that then there would be limits on how multiple, space-time couldn't have all these multiple connections that you mentioned. So that's all I can say. I mean, I don't think we really know what the final answer is, and whether quantum field theory as we know it is really fundamental in the presence of gravity, or whether it has to be modified in some substantial ways. I think even if maybe not even keeping unitarity is still unknown. I mean, I think a lot of questions that certainly people much smarter than me have pondered over about how you can really make a consistent quantum theory of gravity. But and whether you may need to modify the quantum mechanics in some way. So anyway, that's all I can say. I'm not an expert in this.
Okay, thank you, Professor Bardeen. Thank you, Professor Zanelli. So Pato started to write, Pato Majumdar, Professor Pato Majumdar from India, started to write his question. I'll read it. And as he says, the black hole, white hole transition in loop quantum gravity is an adaptation of Baum's model in loop quantum gravity with mini superspace type assumptions. However, in full loop quantum gravity, non-rotating black hole horizons are described by a Chern-Simons theory coupled to bulk gravity described by a spin network. This allows an ab initio computation of the black hole entropy, giving black hole entropy plus a whole slew of unambiguous corrections, beginning with the term logarithm in black hole entropy. Would you like to comment on that, Professor? It's written in the chat. It's a long question.
Sorry, it's the BH capital BH is Bekenstein-Hawking.
Yep, Parto, it's really difficult to hear you. So, Professor Bardeen, would you like to comment on this?
What I can say is that, so most calculations attempted so far are for these mini superspace models, and I think there's good reason to not believe those models, take those models very seriously. But again, I'm not an expert in loop quantum gravity, and I really can't comment on what the really correct approach would be. So
okay,
that's all I could say, really.
Okay, so thank you, Professor Bardeen. We have also a question here from, I don't know if I can pronounce, but let's, Satish Kumar. So what are the conserved quantities invariant with respect to different observers in black hole thermodynamics?
Well, I'm not sure what is meant by conserved quantities. Well, of course, you have electric charge as a conserved quantity. And when you do just Maxwell's theory, the charge of a system is fixed by a super selection rule, right? And you don't consider how the total charge of a system can vary. I mean, it's just is some number. And now that leads to the question in gravity of whether you should treat the energy and momentum of a system in the same way. Now, when you do quantum field theory, you're used to thinking of allowing fluctuations in the energy of a system, the total energy and total momentum, but it seems to me, given that quite possible there should be a super selection rule in that case too, but then what do you do about the gravity Hamiltonian, which is supposed to represent the total energy of is really defined at an infinite radius, in a sense, boundary of the space-time, so again, I think there are very deep questions here, which I am certainly not qualified to answer, but I think they're important questions.
Okay, thank you, Professor Bardeen. We don't have questions anymore registered in the chat, or people that want to talk. If you want, please register. And if you allow me one question, or at least one thing I would like for you to comment on, is what I mentioned in the introduction. So back in 1968, around that date, you proposed the line element of a black hole without a singularity. And after that, many people have constructed theories to give physical support, like nonlinear electrodynamics background to as a basis to these solutions. So, would you like to make any comments or tell us something about that?
Well, so my reason for proposing that model was not because I thought it might be actually realizable. It's just a way of showing that the non-compactness of the Cauchy hypersurface was an essential ingredient of the Penrose Singularity Theorem. That if you allowed so it was really important that you not have Cauchy horizons in the evolution of the space-time for the Penrose theorem to apply. And I didn't consider it myself as a realizable geometry in its own right. So, and I have to confess, I haven't really followed the papers, many papers on trying to make physical sense of something like that.
Yeah, so they are mostly based on what's called the nonlinear electrodynamics.
Yes.
But
no,
okay. Okay. Well, we could talk later on, and I thank you for that. So we have one question. Well, it's as far as I'm aware of, it's from a 12-year-old boy from Portugal. So he wants to make it. I know that because he has participated in previous webinars. It's Francisco. Francisco.
Hello.
Yes.
Hello.
I have a question for you. Were primordial black holes made the same way the current black holes are?
Repeat that, please.
Repeat.
Yes.
Okay.
So were you asking? I mean, so
Where
because he mentioned.
made the same way the current black holes are?
Yeah, I'm sorry, I'm having difficulty understanding.
Okay.
Yeah, so let me try to rephrase it. So in the middle of your talk, I think you mentioned about this primordial black holes, right? And you made the comment on that. And I think what puzzled the boys that, I mean, so what are the difference between this primordial black holes and the other black holes, something like that? Maybe you should tell something about that to him.
Well, so, well, just that their lifetime it could be less than the age of the universe. And so they could be reaching their, have evaporated down to the Planck scale by the present time. That's all. So as Hawking pointed out in his original papers, if you have a black hole whose mass is around 10 to the 15th grams, that and was formed in the very early universe, it would be reaching its final stage of evaporation around this time. So if such black holes existed, you might be able to see they would, as they get down to the Planck scale, the energy of the Planck temperature becomes, the Hawking temperature becomes very large. They're emitting very high energy quanta, and you might hope to detect some little burst of gamma rays. So, so far nobody has seriously proposed actually have detected one. So, unless you, then this is not very helpful. But it's an interesting possibility, and certainly I would encourage people who are interested in how primordial black holes might form.
Yeah, so his question, he wrote in the chat a little, so it's a bit more tricky in a sense. So if these primordial black holes are made the same way as the current black holes are, so, but I think he's very happy with your answer, so he just wrote that in the chat.
I don't know.
Okay, anyway, thank you very much. It has been a really wonderful lecture, as somebody has just wrote in the chat also. So I think we should finish by now. And to finish, I would ask us to again clapping our hands to Professor Bardeen, and after that we end this webinar. Thank you very much. Thank you.